Let's okay, recording.
Okay, well, thank you very much for the opportunity to give this talk. So this particular talk would be very, very introductory, and my goal is to give people just some kind of an idea of what discrete Painlevé equations are about. And the particular approach that I will be explaining is based on a relatively recent, a few years back, joint project with Tomoyuki Takenawa from Tokyo University of Marine Science and Technology, and also Stefan Carstea from Bucharest. And I can't expect people to follow all the details, but I'm hoping that you will get some big picture out of it, and maybe later I'll give a different talk that is more research-based. So this is more of a colloquium level talk aimed at general audience. And I will begin with the motivation for discrete Painlevé equations, which is differential Painlevé equations. And I suspect that many people at the seminar know about the differential Painlevé equations, and indeed last week we heard a talk about their non-commutative generalizations, but still. So if you've never seen them before, and I'll tell you, okay, here is a Painlevé equation and here is not a Painlevé equation, you would be very puzzled. And the reason is it's difficult to recognize a Painlevé equation by how it looks like. Okay, if you look at this equation, it's a second order, nonlinear, ordinary differential equation. It's nonlinear because you have this coefficient here. But what makes it special? What if I change this coefficient 6 to 10, or maybe add another y, do something? Would it still be Painlevé or not? And the reason it's difficult to see is because the Painlevé property, it's not really about equations, it's about properties of solutions of equations. So here I wrote a few very simple examples. This equation, for example, you can just take the integral from both sides to get an equation of the form y cubed is equal to t plus a constant or minus a constant, and then you just take the cube root of the right side to get the solution, and you see the constant appearing, and this constant is a constant of integration or something that's related to the initial value problem, and it's a singularity because when expression inside the root is equal to 0, you have a branch point. So what happens is you have a singularity that depends on the initial value problem, and such singularities are called movable. So for these two equations, again, you see this one is second order, so you have two constants and have, again, movable singularity when t is equal to c1, that will be an essential singular point. And you have this kind of singularity, which is a movable pole. And essentially, Painlevé property of the equation is to say that its general solution, like this is a general solution of this first order equation, has singularities, but only movable singularities are essentially poles. That's a simple version. A more careful version is you want to have single valuedness. So you don't want to have movable branch points or something like that. Okay, so essentially the Painlevé property is a property of existence of a Riemann surface of a general solution with some kind of uniformizability, and that's related to integrability. So that's Painlevé property. And what's Painlevé equations? Well, these are the second order equations that satisfy Painlevé property and have some mild restrictions on the form of the equation. And these equations were classified by Paul Painlevé and his students, especially Gambier. And what they got is about 50 plus cases of second order equations having Painlevé property, of which 6 cases or 6 families of equations were essentially new. Everything else can be reduced to linear equations or can be expressed in terms of solutions of linear equations. So now these equations are known as Painlevé 1 to Painlevé 6. And around the same time in works of Fuchs, there was made a connection between Painlevé equations as appeared in the works of Painlevé and differential equations that appear in isomonodromic deformations, like it was explained recently. So why is this property important, this uniformizability property? The motivation behind the work of Painlevé and his students was really to try to develop a theory of special functions for nonlinear equations. Very briefly, important functions that we study occur as solutions of differential equations, like the exponential function, which is arguably probably the most important function in mathematics, comes from differential equation. Same is true for sine and cosine, for example. And if you look at the equations, you can see here, this is first order linear. This is second order linear with constant coefficients. If you allow non-constant coefficients, you have classical special functions like Gauss hypergeometric, Bessel, Kummer, etc., etc. What's important about linear differential equations? Superposition principle. In other words, if you find a basis in the space of solutions, you can express any other solution as linear combination, and the singularity structure. So you can have singularities of solutions, but they can only occur at points where equation becomes singular. And in the nonlinear cases we just saw, we have this phenomena of movable singularities. And so Painlevé property is really an attempt to sort of talk about equations whose general solutions have this uniformization property. There exists a Riemann surface of a general solution. Okay, so if you look at equations that satisfy Painlevé property, already for first order equations, you notice that something very interesting appears. We get a very important and famous Riccati equation, and probably even more famous differential equation that is satisfied by Weierstrass P function. And this link between Painlevé equations and elliptic functions is actually, there is in Riccati equation, there are deep connections there. So for second order equations, here is the list. And you can see that there are 6 families of equations, and I say families because these equations have some parameters. And also there's some kind of a degeneration scheme where you start at Painlevé 6 and you can, by taking some limits and parameters, go all the way to Painlevé 1. Below, I put the diagram indicating that Painlevé equations actually have solutions that can be algebraic or written in terms of special functions, like Airy function, for example, Bessel function. But that happens only for particular parameter values, okay? And that's briefly about Painlevé equations. What about discrete Painlevé equations? So again, here are some examples, and if you look at these examples, it's very hard to see what's so special about those equations. Why should we be interested in those equations and not something else, okay? They have some features in common. They are recurrence relations, second order recurrence relations that you can either write in this form, or you can write them in the form of a first order system of 2 recurrence relations, which is essentially the same as taking second order ODE and converting it into a first order system, okay? So the classical example is this second order recurrence relation. It's non-autonomous because you can see that the coefficient here depends on the step n of the recurrence. And this equation is almost 100 years old now. And it originally occurred in the study of orthogonal polynomials in the work of Shohat. And then later it occurred when Brezan, Kazakov, and separately Gross-Migdal were looking at some toy 2-dimensional models of quantum gravity, and they got this recurrence relation there. And showed that after particular scaling, this equation has a continuous limit, and this continuous limit was Painlevé 1. So it was natural to say, oh, this is a discretization of Painlevé 1. It's a discrete analog of Painlevé 1. Let's call it a discrete Painlevé equation. And there were some other examples. And in early 90s, a group led by Alfred Romani and Basil Grammaticus started creating a lot of equations that had this property that they had a limit towards differential Painlevé equation. And they called them discrete Painlevé equations. The strategy that Grammaticus and Romani were following was they would start with an autonomous analog. And what happens is, if you take differential Painlevé equation and try to look at what happens when this equation becomes autonomous, in a sense, you end up with equations on elliptic functions. And there was a discrete analog of this known as QRT map, and they tried to deautonomize or make it parameter dependent, and then imposed a certain condition that is known as singularity confinement. So this condition. And for a while, it was thought that singularity confinement may be an analog of Painlevé property in discrete world and be analog of integrability. Turns out very quickly that it was not the case. There was an example constructed that satisfied the singularity confinement condition, but was non-integrable in the sense of algebraic entropy. It's a famous Heter-into-Vialet equation. And turns out that geometric theory explains what's happening there. And that's really a realization that essentially was done by Sakai, who showed that discrete Painlevé equations should really be thought of as geometric or algebra geometric models, objects. And that explains why discrete Painlevé equations look the way they look. Also, the connection between discrete and differential Painlevé equations. And that's really, I think, one of my main messages for today is to show or try to convince you that this geometric approach is actually the correct one. It's the right language for studying these examples, and maybe not just in discrete, but also in the differential case. But Sakai classification scheme is quite complicated. The origins of that are in the work of Akamoto. And what Akamoto did was essentially this. You start with a differential Painlevé equation. You can rewrite it as a first-order system. Turns out that this system is Hamiltonian. In other words, you can find out a function h where that generates the dynamics, but this Hamiltonian is non-autonomous or time-dependent. And if you want to study solutions of this equation or Painlevé transcendence, one way to parameterize them is by initial conditions. So you try to create the space of initial conditions, but turns out that if you want to allow poles for the Painlevé property, you want to allow initial conditions that also can be poles. And for that reason, you need to just compactify and go from C2 to P1 cross P1, okay? But as you do that, it turns out that you get additional points where multiple solutions collapse together, and you need to fix this somehow. And there is a procedure in algebraic geometry known as a blowup that separates trajectories going through the same point. So then Akamoto constructed what is called the space of initial conditions over here. So basically you take C2, you compactify to P1 cross P1, and then you have to remove a certain configuration of curves known as vertical leaves along which the motion is vertical. Let me maybe draw a quick picture. So you have time direction here. You start with possible initial conditions, and you want to look at your solution. That would be Painlevé flow. Then you add some boundary curves here, and then as you do that, there can be, let's say you added this additional curve here. There may be a point here, so that if you start at this point, the flow is perpendicular to the time direction. So you have a flow of a vector field, but that flow of a vector field does not correspond to the solution of your differential equation. So you want to throw these points away, and you get a certain configuration of curves that you throw away. This is called the configuration of vertical leaves, and the resulting geometric object is called space of initial conditions. And Sakai showed that actually, if you study symmetries of the spaces of initial conditions, that's how you get discrete Painlevé equations. And he generalized that to all possible surfaces that satisfy certain requirements, and said that everything that we can get from these symmetries should be thought of as a discrete Painlevé equation. Okay? So the language of his classification is like this. So I'll show you the classification scheme. So you see it's pretty involved. Not that only you have 6 equations, you have a lot more. You can see the Painlevé differential equations appearing here. So that's the diagram I showed you a little bit earlier, except that it needs to be extended somewhat. There are versions of Painlevé 3 that have different properties for some degeneration of parameters, some parameters becoming 0. Okay, so it's still called P3, but the geometry underlying the equation is different. The letters that appear here are letters labeling certain configuration graphs known as Dynkin diagrams, or more particularly affine Dynkin diagrams. And you have this dual picture of affine Dynkin diagrams. Like, for example, you have a pair here. This here you have geometry, and here you have actually that's maybe a bad example. Let me maybe choose something here. So here you have geometry, and here you have symmetry. So they go together. And geometry is like your configuration space, and symmetry is like the origin of your dynamics. Okay? So if you look at this diagram, you start realizing why there were problems in the naming scheme, because here is Painlevé 2, it lives in this part, and you can do the limits from here and from here. So you have 2 different discretizations of Painlevé 2 that are non-equivalent, and geometry helps explain why. Also, you can start at the same place and sort of do different kind of limits, and then you end up with different equations living on the same geometry. So that's how the Sakai degeneration scheme is going. So differential Painlevé equation or discrete Painlevé equation is characterized by a pair of affine lattices, and you obtain the configuration space by taking P1 across P1 and blow it up, create configuration space, and then study symmetries. And symmetries generate something known as Cremona isometries, or some transformations of the family. And you combine these Cremona isometries into elements that correspond to translation in some sense. And that's how you get discrete Painlevé equations. So my goal is to try to explain a little bit of what's happened in this picture. Okay, so that was motivation. Now, introduction. So we will talk about discrete integrable systems. Two-dimensional discrete integrable systems. So how can you think about a discrete integrable system? You pick up some space, X, and you pick up a mapping phi from X to X. And then you get your system, you get the trajectory of your motion by iterating your system, just applying phi recursively, okay? What do you want from this mapping? You want it to be reasonably interesting, a nonlinear mapping, but you want to impose integrability condition, like whatever that means. You also probably want the mapping to be reversible, so you can not only just go forward in your dynamics, but should be able to sort of go backwards in your dynamics as well. Finally, you may want your mapping to be autonomous or non-autonomous. What does this mean? So here, you see, I showed you two steps of the dynamics, and I need to tell you about the notation convention in discrete dynamical systems. Usually, if we want to study the map, we call the current point simply by X and denote the next point by X bar and the previous point by X underline. That should not be confused with complex conjugation, but that's a standard sort of convention. So how do you take this autonomous picture and make it non-autonomous? You say that your surfaces, your configuration spaces may also depend on the step and the dynamics. Of course, you don't want them to be like completely different. So what you have is some kind of a family, and you have a motion in this family. And your mapping also can depend on this parameter. Okay? How can a mapping depend on the parameter and at the same time sort of be the same mapping? You can think about the mapping phi. Phi. It depends on the point, and then there's some parameters, A. And these parameters may vary. So the shape of the mapping will be the same, but the concrete mappings may differ. I'll show you some examples a little bit later on. Okay, so the goal is to start with an autonomous mapping known as QRT that has a very simple geometric construction, and then somehow wiggle it a little bit so that it becomes non-autonomous. So that is called de-autonomization. And in this way, you get some discrete Painlevé equations. And once you sort of see how some of them appear geometrically, you can push it and try to do the complete classification. Okay, so let's look at the QRT map. It's a very beautiful example. The QRT here stands for the three people who sort of define this mapping, or a family of mappings, Quispel, Roberts, and Thompson. And I will give you a very simple geometric description of this mapping that it essentially follows the paper by Terutsuda. So this is what you do. You start on P1 cross P1, start here, and on the pick up an affine chart with local coordinates little x, little y. And then in this chart, you write down the polynomial equation. So since now we have two variables, we can talk about the degree of this polynomial in a variable x or variable y. And the requirement is that both degrees are 2 and 2. So such a curve defined by this equation is called a biquadratic curve. Okay. So you look at this biquadratic curve, and there is a notational convention that you can put all the coefficients inside the matrix, and then you can think about the curve written in this way, the curve equation. So I start with a matrix, 3 by 3 complex matrix. I am not requiring that it's non-degenerate or anything special, although sometimes I may want it to be symmetric. And then you have a curve, okay? So an important fact is that a biquadratic curve on P1 cross P1 generically is an elliptic curve. Okay, we usually think about elliptic curves as cubics, but what happens is if you have P1 cross P1, it's actually different from P2, but what is called birational equivalent. So there is a rational map from P1 cross P1 that is invertible, and inverse is also a rational map. There will be points where they're not defined, but they will give you one-to-one correspondence on everywhere dense set, open set, and Zariski topology. And if you have a cubic curve here, it becomes biquadratic curve here. So elliptic curves appearing as cubics on P2 correspond to biquadratic curves on P1 cross P1. Okay, so biquadratic means that it's quadratic in the x and quadratic in the y. In other words, if you pick up a point on this curve and then look at the vertical line or horizontal line, they should intersect at 2 points. So the point that you're starting with and another one. Okay, so you can define two involutions that flip these 2 points, ry, that flips the y coordinate for a fixed x, and rx, that flips the x coordinate for the fixed y. Okay, by themselves, of course, they don't generate any dynamic, but you can combine them. You can start here, and then you can go here, and then you can go here, and that's sort of your next point. You see here, I'm using my x over bar, y over bar notation convention to sort of indicate how it goes. Okay, so here is a picture for you. This is an example known as the Linnaeus map, very interesting example that I will not talk about, but I wanted you to see how the dynamics goes. So this is the first point over here, on my first point. This is my second point. This is my third point, fourth, fifth, yeah, and somewhere here will be number 6. I'm starting to lose it, sorry. Okay, anyway, so we have this kind of motion, and if you look at this picture, you can actually see that this is some kind of a slice of a donut that you see. So that's a real slice of an honest elliptic curve. And over here, you can see the first 30 points of this dynamic. So because it's an elliptic curve, you can think about it as a fundamental parallelogram. And turns out that this dynamics on this fundamental parallelogram is essentially you pick up some vector, and then you translate on this vector, and this is your trajectory. And that's exactly what is really well explained in this paper by Tsuda. Okay, but this is not a QRT map. It's sort of the first step towards building the QRT map, because for the QRT map, you need the configuration space to be the whole plane. And for that, you need to extend to P1 cross P1. And this is how you do it. Instead of one matrix, you take 2 matrices. Take matrices A and B. And you create a one parameter family of equations. To this one parameter family of equations will correspond a one parameter family of curves. And such a one parameter family of curves is known as a pencil. So we have a pencil of biquadratic curves. Of course, it's parameterized by these coefficients alpha and beta up to a common multiple. So it's a P1 parameterized family of curves. Okay. Then if you pick up any point, it's easy to use the coordinates of a point to find the parameters alpha and beta to get the curve passing through this point. So in this way, you sort of cover all of your P1 cross P1 by this family of biquadratic curves. But there's a problem. These curves will intersect. And in general, there will be, not in general, there always 8 points of intersection, except that for some parameters, they can collide. But generically, you have two curves, you get 8 points at the groove. Sorry, slow down. If you take two biquadratic curves, intersect them, number of intersection points counted with multiplicities will be 8. And so all points, all curves in this family will be passing through these points. So such points are called base points of the pencil. And here is the problem. So suppose you have your initial condition here and you jumping around and you jumping around, and then at one point you end up here. Then you don't know how to continue because all of the curves pass through this point. Okay, so the way to fix it is, again, you use the same blow-up procedure to separate these different curves, and as a result, you change the geometry. So you change the geometry of your P1 cross P1, you create some more complicated rational algebraic surface, but on that surface, you regularize your dynamics and everything becomes well-defined. So you get this rational elliptic surface. The word rational means you get it from P2 or P1 cross P1 by blow-ups. It's a surface birational isomorphic to a complex projective plane. And on this surface, you have fibration. So I'll show you a little bit later. But what can happen is you can get singular fibers on the surface, and the number of singular fibers, or the types of singular fibers, there is a classification due to Kodaira. There are 22 types. Turns out that this 22 types is exactly what we see on this diagram in some sense. Okay, so we will see how this happens. Okay, but before, I want to simplify my life a little bit and define what is known as a square root or half of the QRT map. So your QRT map is a combination of vertical flip with a horizontal flip. What you can do is you can introduce an intermediate flip that just switches the x and y coordinates. Let's call this flip sigma. Then this map can be written as a square of a simpler map phi that's known as a half QRT. There's a little bit of a catch there. This transposition not only switches the values of x and y, but it also transposes the matrices defining the curves. So if you have a symmetric case with A and B being symmetric matrices, you have an honest half or the square root of the dynamics. In the non-symmetric case, you have two closely connected equations, but I'll assume everything is symmetric. So then you can study this map phi, and you can easily eliminate alpha and beta, and then solve for x and y of some functions f1, f2, f3 that you can get by essentially taking the cross product for the x with the matrix A and then cross product the same with the matrix B. Okay, so you get this dynamics. By construction, this dynamics has a conserved quantity because we think on the curve. The dynamics I define so it preserves this parameter of the pencil over here, and we have conserved quantity. Okay, so we will study this mapping and then get Painlevé equations by doing this de-autonomization of a mapping for some concrete example. And this is the concrete example that I want to take. Matrices A and B. This is how my matrix A looks like. This is how my matrix B looks like. Here, little a is some parameter different from 0 plus minus 1. you get this explicit mapping. And that's the corresponding pencil. It's parameterized by this value of k, and it's an exercise to show that this value of k indeed is fixed with the dynamic. And now you can see the points. There are two curves. One is little xy. The other one is this curve. And if you want to see where these curves intersect, first of all, what is the curve xy? Well, it's a reduced curve. It satisfies the equations either x is equal to 0 or y is equal to 0. So you have something here and something here. However, I want to think in terms of biquadratic curves, and this one is not. This one is linear in x and y. So the reason for that is I need to work on P1 cross P1 and work in homogeneous coordinates. So there, if I introduce my little x to be something like x0 over x1, and same for y, I have to rewrite the equation of this curve as x0 over x1, y0 over y1, but I need to multiply it by x1 squared, y1 squared to homogenize it. It becomes x0, x1, y0, y1, where x0, x1 are homogeneous coordinates on the horizontal P1, and the same for y0, y1 for vertical. So your curve actually picks up these two lines at infinity. And this is your first curve. This is my gamma A. And turns out that gamma B is also sort of a reducible curve going like this. But this I will not going to explain, something like that. I'll show you a careful picture later. But you can see some points of intersection over here. And for example, this point will correspond to y equal to 0. What happens when y is equal to 0 in this equation? You have 0 in the denominator, which really means that you map to infinity, except that if x is equal to a, x is equal to a, y is equal to 0, you have the 0 over 0 property. You don't know what to do. And that's exactly when different curves in the pencil collide. So you need to fix this using blowups. And there will be 8 points like this, okay? And as you fix that, you build a new surface X, and a very important object that we need is called the Picard lattice of X. So let me remind you what that is. So by definition, Picard lattice is just a group of equivalence classes of divisors, where divisor group is generated by irreducible hypersurfaces, or in the two-dimensional case by curves, and the equivalence relation is given by modular principal divisors or divisors corresponding to rational functions. It's very easy to see that this abelian group for P1 cross P1 is generated by classes of horizontal and vertical lines. So it's just a two-dimensional free abelian group. Okay. And also it is equipped with intersection product, which is an inner product where you really count the number of intersections, like two curves that correspond fixed values of x. Over here. So for a biquadratic curve, its class is actually 2hx plus 2hy, saying that it's quadratic in x and it's quadratic in y. There's an important remark. So when you look at this divisor classes, you can look for a divisor class that corresponds to the canonical element or differential form of the top degree. On the surface, it's a differential form, differential 2 form. And for example, you can take the form that in affine coordinates is just dx wedge dy. If you look at it in different charts, you see that you have poles at infinity for x and y with multiplicity 2. You can choose a different form like this. Then it will have poles along these two lines and along these two lines, just like my curve. So this is called anti-canonical divisor class. It's a poles of some two form, and two forms on the surface correspond to symplectic structure. So really, biquadratic curve you can think of as a location of poles for some symplectic form. Okay. We need the duality here because from poles we want to go to zeros. So the object that we're interested in is the anti-canonical divisor class minus kx. Okay. So here it's just corresponds to the class of our biquadratic curves. Using the intersection product, by the way, over here, you can see that indeed two biquadratic curves intersect at 8 points on P1 cross P1, or you want to look at cubic curves that will be intersecting at 9 points if you look at P2 model. Okay, now how do you fix the singularities by blow-up? Very, very briefly, it's a standard singularity resolution procedure in algebraic geometry. Normally, if you have a point on the plane that is different from the origin, you can think about it as an intersection of horizontal and vertical curves. But you also can just use a vertical line and the line through the origin, or horizontal line and the line through the origin. In other words, you can parameterize this point by its x-coordinate at the slope of a line going through that point and the origin. So you introduce then, in addition to coordinates x and y, another coordinate which corresponds to the slope, because lines through the origin are really what is element in P1, right? And you impose the equations that this line goes through this point, get some surface. And if you think about what the surface is, away from the origin, there is a one-to-one correspondence because there's only one line. But at the origin, all lines go through. So if you think about this mapping pi from the surface in C2 cross P1, this is my x and y, and this is line that records the slopes. So for the center of the blow-up, you have the whole curve. And for any other point, it's a bijection. And the nice thing about the blow-up is it sort of takes all, in this picture, straight lines going through the point and separates them by lifting them in this third direction of slopes according to the slope at which they enter the center of the blow-up. Okay? Algebraically, what happens is you just introduce two new charts, little uv and capital UV, and it's just a coordinate substitution, like this. And the picture is like this. Of course, it's a real picture, not a complex picture. We really need to be thinking in terms of complex variables. Another important thing here is the notion of a total transform and proper transform. So for proper transform, you take the line. If you take its pre-image, it will be a line on the surface together with the pre-image of the points where you blow up or of the central fiber. So you say, oh, okay, we will call just this line a proper transform. Then another thing is intersection theory. So if lines were intersecting downstairs and not intersecting upstairs, the consequence of this is that the central fiber should intersect with it with multiplicity -1, or have a self-intersection -1. If you think about it naively, geometrically, like intersection of curves, it doesn't make too much sense. But if you think about it as in the correct way, and that would be the Chorn class of the normal bundle of the embedding of this central fiber into the surface, then it does make sense. It basically says that the central fiber of the blow-up is rigid and doesn't have infinitesimal deformations. So this self-intersection number will be important for us. Okay, and I will visualize everything in this strange way. So I will visualize my C2 as just a picture of a plane. And if I blow up this point, I will just draw the lines being separated, even though I shouldn't really be drawing them curved, but it's convenient. Okay, so when you do a blow up at this point, it's like you do this new line corresponding to the central fiber of the blow up. It may be worth pointing out that this E here is actually P1. So really what I'm doing is I'm having my surface X, and if I'm doing a blow up at this point, I'm sort of blowing a bubble here, or instead of a point, I put in a sphere, but I don't know how to draw it really well. Okay, so this is really a sphere, if you think in terms of complex variables. Okay, so back to our surface. We had this QRT map, and it had 8 bad points. You blow it up at these 8 bad points, and now you create a surface. That surface will be like 2 spheres, because P1 is a sphere, so P1 is a sphere. So you have 1 sphere multiplied by another sphere, and at 8 points of this product, you will also have 8 spheres of the blow-up. It's like, you know, you take a torus and you change a point to like a circle, but only you do it for not for circles but for spheres. So you get this. You have this surface. Can think about it like this. This would be your surface over here. This is your surface X. There is a mapping from the surface X to this parameter of the pencil K. And generically, you have an elliptic curve, and you have this QRT dynamics on elliptic curve. And then there is a bunch of fibers known as singular fibers. When you do this blow up, your Picard lattice, it will now be a span of your coordinate classes hx and hy as before, but also you add these classes e1 to e8 for each of the blow-up points. And you can compute, it's a pretty straightforward thing, the induced dynamic on the Picard lattice. It will be some linear map of this rank 10 integer lattice into itself. Okay? So, and then, so you have this elliptic fibration that can have singular fibers. These singular fibers are labeled by this Dinkin diagram labels, and I'll explain this example that we're going to look at next, and look at de-autonomization. So this is what we have. So we start with a QRT map that is defined by taking 2 biquadratic curves and taking a pencil generated by these curves, and they will be passing through 8 points. But these 8 points are actually special, because if you take generic 8 points, you don't have a family going through them. You have only a single curve going through. So what you can try to do is you can try to take these 8 points and preserving the dynamics in the sense of having the same linear map on the Picard lattice, just shift these points a little bit. Like, for example, here I shifted them along the generic elliptic fiber. Here I shifted them along the special green fiber, or shifted them along the blue fiber. Okay? If you do that, that singular fiber becomes the unique anti-canonical divisor. And then the intersection configuration of its irreducible components is described by a affine linking diagram. Like over here, you can see that I have 4 lines that are pairwise intersect like this. So this is the intersection configuration for the blue lines. And this graph is known as a affine linking diagram A3. The usual linking diagram A3 is like this. And for affine, you add an extra point, and that's how you get this. Okay? So I will look at the autonomization with A31 fiber, and that creates an equation known as Painlevé equation. Okay, so how can you do that? This was my mapping. This was my mapping, and remember, it was half of the QRT, so I need to square it. So in this notation, I just add a double bar. So here. Add a bar everywhere. And then y double bar is x bar. And then I realize that, oh, okay, so where I have an x bar here, I can just put y double bar. And y double bar is x bar. So I can just put this whole thing here. So this is my y double bar, and this is my x double bar over here, where for x bar here I can just put y double bar. Okay, so and then what you can do, you can say, okay, these points, 8 points were defined just by a single parameter array, and that's what made this point special. What if instead of this a's, I just put some arbitrary coefficients like, so my y double bar is actually g bar. So y is g, so that's g. It was 1 here, but convenient to put some coefficients b3, b4. And so x minus a is like f minus, and I call this b5. So you create this mapping, okay? And the way you should be thinking about this mapping is that's a non-autonomous automorphism of a field C that has 8 parameters and 2 variables. So variables change according to this equation, and parameters also evolve. Let me ask a quick question now. How much time do I have? Is it an hour, is it an hour and a half, or is it somewhere in between? Vanya, Andrei?
Hour and a half, as far as I know.
Okay, okay. Then I'm not going to rush. But probably I need less than an hour and a half, but more than an hour. Anyway, so this is the equation. Notice that my de-autonomization was extremely naive. I just picked up 8 points that were special and changed special to where are my points? Here. You see, I basically what I've done, I changed this A to B1, this to B2, and something like this. Okay, very naive, and kept the same equation. If you want to do something more interesting, it's complicated, but this naive works for us here. So you get this mapping, you get this equation, and again, you have the same base points that again you need to fix using the blowup, but the new feature is that your points, now the coordinates of the points are moving with the dynamics. Like coordinates of the first and second point are multiplied by some strange number q, expressed in terms of parameters here. It's very unclear why it should be that number, but and so you really go from one surface to the next and sort of keep going like this. Okay. So this is the schematic picture. So these 8 points are now, you blow them up, and your anti-canonical divisor is again this 4 lines. That's by construction. That's what I chose. So what happens is you're fixing the configuration on which your points lie, but you allow the points to move in this within this configuration, okay, with the dynamics. And you go back to the Picard lattice, which, as I mentioned, after the blowup has this classes of central fibers of blowups, and your anti-canonical divisor decomposes like this. These are the four red curves. And this notation over here, that's the proper transform. So this minus doesn't mean that you're subtracting something. It just says that you don't include the full pre-images of the blow-up points. You just look at the proper transform of a line going through these points. Like if you take the full transform of this, you will be getting this and also this. And the proper transform of this line would be just this. That's what this notation says. And then you pass to equivalence classes. I indicate that by going from straight letter to script letter. Okay, so you get this picture. And turns out that this is a part of a general theory. How does Sakai theory work? You start with P1 cross P1, blow it up at 8 points. You get the anti-canonical divisor class. It has this property that minus kx squared is equal to 0. So in the whole of Picard lattice, Px, what you want to do is you want to restrict your attention, sorry about this, to the orthogonal complement of the anti-canonical divisor class. And that becomes a root lattice of type E8, affine E8. And we say that we have a generalized affine surface of index 0 if in that class there is a unique divisor. Okay, unique anti-canonical divisor of what is called canonical type, so that its intersection multiplicity or intersection with the class itself, for which component is equal to 0. Then classes of components generate for you sub-lattice and Picard lattice known as a surface sub-lattice. You can look at their orthogonal complement, and turns out that it's also a root lattice and has a root basis alpha I. And both di's and alpha i's will be described in terms of affine Dynkin diagrams. And if you have an affine Dynkin diagrams for alphas, you can build an affine Weyl group, starting with generators, this alpha i's. That should, from alpha i's, I need to go to wi's, I explain that. So you get this affine Weyl group, and that's symmetries of the surface. You need to extend it, but let's not worry about this now. So, and this affine Weyl group, it has translations. So if you take elements that correspond to translations, you get dynamics, like infinite dynamics on your symmetries, and these dynamics can be pushed to the level of actual surfaces, and that's what the discrete Painlevé equation is. So let me now try to explain this in a little bit more detail. So this is my example. Remember that picture that we had. It corresponds to this affine Dynkin diagram where these are the classes of points. If you look at elements that are perpendicular to these in Picard lattice, you can compute, and you see that there is a basis, and this basis is also a root basis, squares of which element is -2, and that's the intersection diagram for this. Okay? Now, you can use this to build a Weyl group, a affine Weyl group, where you put to each node of the diagram, in correspondence an element of the group, and you look at the group generated by these elements together with relations, and the relations are this: each element is an involution. If the nodes of the diagram are not connected, these involutions commute. If the nodes are connected by a line, these involutions satisfy the braid relation. You extend that by automorphisms of either this diagram or its dual. It can be shown that it's the same group. And here it's easy to see that this is just the groups of symmetries of a square. So you build up this group. And then this group acts on Picard lattice by reflections. I'm sorry, I never wrote it somehow. So what happens is you have your element Wi, it acts on peak x by doing the following. So think about the following picture. Here is alpha I, here is a perpendicular surface to it. And if you take a vector v, you can reflect this vector like this across the perpendicular surface to alpha I. So you think about this vector as some class in the Picard lattice C. So the action is Wi, the class C, is just C minus twice C dot alpha I dot alpha I. And because these are roots, alpha I square is 2, except that here there is a non-standard extra minus, and you get this action Wi takes a class C and sends it to C plus C dot alpha I. So this is action on Picard lattice, and you can push it to the level of surfaces. Okay, so this is what happens. You have a surface for some value b, surface for some value x b bar. You can construct the mapping phi between those surfaces such that this mapping phi induces the mapping Wi on peak. Peak of x and peak of xb, they're all isomorphic, so the surfaces are different, but their Picard lattices are all the same, not just the lattice of rank 10. So you can construct this. Maps, and this is known as a birational representation of our affine Weyl group. So you see here parameters change in some strange way, and variables change. Okay. I will not tell you how this is done, but the important thing is this. We have this mapping. So this mapping over here, this is what is known as QP6. Right now, you see this mapping as just a mapping in variables f and g on P1 cross P1 to P1 cross P1. You regularize by blowups, and you get this family of surfaces x parameterized by this variables b. In each family of those surfaces, there is this anti-canonical divisor that is completely fixed. But the points of the blowup are moving on this anti-canonical divisor, and so the surfaces are different surfaces in the family. So, and then you can compute the action on this map on the Picard lattice. So it's written here, just some linear map. And then you can see how it acts on the surface and symmetry. So on the surface, it is some kind of automorphism of the surface lattice. That's why we need to extend our affine Weyl group by automorphisms. And on symmetry roots alphas, what happens is it is a translation in this direction, sort of in the scale of anti-canonical divisor class. What that means is that alpha 0 bar is alpha 0, but alpha 2 bar is alpha 2 plus delta, where delta is the anti-canonical divisor class. Okay, so this is discrete Painlevé equation. That's sort of the definition. So you can see that this definition is now miles away from nonlinear maps and everything, but that's the definition. Okay, so a discrete Painlevé equation is this discrete dynamical system on the family of surfaces that you get, generated by a translation in the symmetry sublattice of the corresponding surface. So now let me go back to this diagram and try to explain what is going on here. So if you start with, if you start with just 8 points in general position, you will, they will all lie on a smooth elliptic curve like this. This elliptic curve will have the largest symmetry group, affine E8, and translations in this affine symmetry group will generate elliptic discrete Painlevé equation. It's called elliptic because once you write it in coordinates, the coordinates of the mapping, the coefficients of the mapping will be written in terms of elliptic functions, and the way this elliptic functions will change is additively in the argument. Okay, so after that, you can try to start degenerating your curve. So for example, you can take this cycle and you can pinch it, or you can take 2 cycles and pinch them. And if you take these 2 cycles and pinch them, you will get something like this. You get like one sphere and the other sphere with a nodal intersection with like 4 base points living in one and 4 base points living in the other. And that would be this surface over here, A11, okay? And corresponding to the surface A11 is the symmetry group E17. You can construct the birational representation of this group E17, take translations in the group, and use the representation to write down exactly how the dynamics will go in terms of coordinates. Okay, so we are here. So group A31, there's a particular translation, and corresponding to it is the symmetry D51, and then I can write down the mapping. So basically, the main message is the classification of discrete Painlevé equations is this. You classify all possible degenerations of 8 points in the sense of generic one is one curve, and then you try to degenerate and it breaks into components. You will start having sort of points merging, becoming infinitely close, etc., up until the very end where they all merge into one single thing. And that's the possible 22 cases. And then for each configuration, you can build symmetry, and from symmetry, you can build dynamics. So now let me try to explain briefly how this can be done. So here is the reverse process. Okay, So I say someone comes to me and says, I want to know what is a discrete Painlevé equation of surface type A31, symmetry type D51, corresponding to the translation vector T 0, 0, 1 minus 1, 0, 0, like this. Okay. I start by building my surface A31, and I build the simplest possible model, like this. Then I start building up my group, D51, and then I need to write down my translation in terms of generators, like the product of W's and sigmas, where W's are reflections and sigmas are automorphisms. So the question is, how can I find the word in the group that corresponds to this translation? And there is a procedure which basically says this. Okay. I start with this vector, and then I add that gauged by class of anticanonical divisor that I can write down in terms of my generators. So from this diagram, I can say that delta, which is antican class, is A0 alpha 0 plus alpha 1 plus 2 alpha 2 plus 2 alpha 3 plus alpha 4 plus alpha 5. These numbers are essentially the coefficients of the null vector of the Cartan matrix corresponding to this affine Lincoln diagram. Okay, so, and this is alpha, and this is how I acted. And you notice that of all the roots, one is negative. So what you do is you act by the corresponding reflection, and now that root becomes positive, but different roots become negative. So you act by corresponding reflections, and at the end of the day, you go back to the standard root. And that is essentially, you need to read it backwards, but this is the representation. So details are not important, but what's important is that there is an algorithm that, given the action on Picard lattice and the corresponding translation, allows you to rewrite it as a word of generators in the group. And conversely, you can start with your configuration of points and variables f and g, and just dress it by the action of this composition of basic maps that we constructed. And you do that, and at the end of the day, this is your QP6 equation of Dzhamay and Sakai, and Q appears in the process. Okay? So that's sort of going there and back. Okay? I am skipping quite a few things. Like, for example, turns out that this Q is not arbitrary, but something called the period map of the anticanonical divisor class. And if you compute the values of period maps on symmetry roots, you get parameters AI that are canonical parameters of your surface, et cetera, et cetera, et cetera. But I hope that the gist is clear that discrete Painlevé equations originate from birational representations of affine Weyl groups corresponding to blowups of P1 cross P1 at 8 points. Less than 8, your symmetry is not affine but finite, and you get Delpezza surfaces. More than 8, you have other analogs of Weyl groups, and you have chaos. So in particular, that example that I mentioned ages ago of a space that satisfies singularity confinement but is not integrable is the one where you had to do the blow up at 14 points to regularize the dynamics, and it was non-integrable. So that's that. And essentially, this is an extremely condensed content of the course that I'm teaching here at BIMSA. And if you find this interesting, I encourage you to maybe try to attend the course or just view the lecture notes and the videos for the lectures. I will conclude with a simple application. It is an example of a discrete version of Painlevé equivalence question or Painlevé identification question. I have two equations. One is nice, despite how it looks. The other one is really not nice. Both are rational, but this one, alpha and beta, are these rather complicated expressions where you have R1s and R2s are, again, some other complicated expressions. And you suspect that this equation may be the same as this equation. Just need to change variables. But how do you change variables? How can you guess a change of variables that somehow takes this nasty one and makes it nice? So both of them correspond to different Painlevé equation of this type with this symmetry group. The first one we got by trying to study elementary Schlesinger transformations of Fuchsian systems, but Fuchsian systems that don't have any continuous deformations for Schlesinger equations, only have sort of discrete Schlesinger transformations. And the second example is like the standard discrete Painlevé equation in this family that was obtained from QRT map by Grammaticus, Romani, and Otto. And the answer is, yep, here's a change of variables. Okay, how to get this change of variables? We do all these computations, we identify the translations. We write the translations in terms of generators, and notice that they're not the same, but they're the same up to conjugation. And this conjugation gives you a change of variables, and you do. Okay? So there are many, many examples of discrete Painlevé equations appearing in orthogonal polynomials, in integrable probability. They describe gap probabilities in determinantal point processes and things like this. And this geometric technique turns out to be a very simple and direct way of answering the identification problem. There are lots of papers in in orthogonal polynomials where people say, we got this recurrence, we kind of suspect it's discrete Painlevé, just not sure how to find it. And this process just works. I will conclude by some references. So probably in order of importance, the most important one is this one. It's a very, very nice survey by Kajiwara, Naomi, and Yamada on geometric aspects of Painlevé equations. I have to say that this whole theory was created essentially by the Japanese school with Akamoto and Sakai doing geometry, and Naomi, Yamada, and also Kajiwara doing symmetry, developing symmetry approach. My approach is more geometric, but and I'm following Sakai maybe a little bit more, but both approaches are really have to go together. And this is also a very, very nice book by Naomi that talks about a relationship between discrete Painlevé equations and differential Painlevé equations. And the link is you have these translations, and your translations there on the lattice. So in fact, for each configuration space, you have lots of different commuting flows given by discrete Painlevé equations. And after a while, some of them will start having continuous limits, and that's how you go from discrete to differential Painlevé equations. And the flows that were commuting with it before the limit, after the limit, essentially become Backlund transformations of differential Painlevé equations, and that's how a lot of discrete Painlevé equations were also identified. The approach that I described was following this paper with Takenawa-san and Stefan, where we try to give a bit of background and explain how you can actually do this de-autonomization. It's not easy, and there are some quite advanced techniques. It's not as simple as let's just change the coordinates of the points to arbitrary parameters. And finally, number 0 here is Sakai's paper, which essentially is the complete theory of discrete Painlevé equations that he did in his PhD thesis. But this paper is difficult to read. After you understand the theory, you read the paper and you sort of recognize how beautiful and fundamental it is, but it's impossible to, at least for me, it was impossible to learn the theory from that paper. And I apologize, I forgot, there is a very nice book on by Hans Dustermaat. It's called Discrete Integrable Systems. And he only talks about QRT. There's like 600 pages about QRT. So a lot of details are there. Okay, I think I'll stop at this point, and I think we still have time for questions. Thank you.
Okay, thank you. Before comments and questions, I want to say that we hope that next Anton talk will be in May in our in our seminar. Okay, now any questions, comments?
Yeah, maybe for this talk, let me say, I can show you 2 examples, one from discrete orthogonal polynomials, the other one from integrable probability, where discrete Painlevé equations occur.
Okay. So we have not questions. Maybe Anton, maybe you can add the reference on your course in BIMSA to these slides.
Mm-hmm. Okay. Yep.
Okay, and send it to me. Okay, thank you. So bye-bye. We can finish our